So, say you have an artificial intelligence agent in a large area here at point A, and you want to get the agent over here to point B on the other side of this obstacle. You start to think of ways to do this, and the first thing you think of is a pathfinding algorithm called A-star search. But you remember that A-star works best with smaller areas. This area is far too large. Well, you could use weighted A-star search instead, but that has some trade-offs with how good the solution is. So you think of different ideas, and think some more, until, what if you randomize weighted A-star? What could possibly go wrong? So you go back to your area with the agent. We can instead look at it as a grid, and this grid can also be seen as a tree, where the root node is the starting cell of the agent, and every other grid cell is a successor, with the end cell somewhere down the tree. The goal here is to find a path from A to B. In order to search for a path, we want to find a certain number of random successor cells, which we will call K, that are at most a distance delta away, and try to find a path to each of these cells. Now, what do I mean by distance delta? Well, say we want to find the distance of this cell from the root. The distance is 1, 2, 3. And this cell is distance 2. Pretty simple. So, for this example, let's say we want to find 8 random successors within a delta 20. So our random nodes are these. And on our grid, our randomly chosen successors are here. Now we want to try to find a path from the starting position to each of these nodes using weighted A-star search, starting with the highest priority cells. However, we're only interested in paths to these nodes that we can find easily. If we go past a certain threshold, say a time limit or an expansion limit, we stop and move on. So now we find a cell with a high priority and we expand. Then we go to the next, and to the next, and so on. When we're done with the first set of successors, we can move on and start expanding the cells in the grid that we've just worked towards. So we choose more random successors, and we expand. Choose more successors, and expand. Occasionally, we'll pass our threshold for a cell expansion. Other times, we find paths that are just plain bad that we don't want to take, so we label them as a void and we ignore them. Eventually, we will find an expansion that can see the goal cell in the grid. This takes priority, of course. So we expand this cell and find path to the goal. Now we just follow the path all the way back to the beginning, and we have our path from A to B. And this is what Maxim Likhachev and Anthony Stentz called R-star search.